Okay, welcome to lesson 3 in our mini unit that's kind of tacked onto unit 5. So this is going to cover the first part of inverse functions. There's actually a lot that we can do with inverse functions and kind of had the option of trying to cover all of it in one lesson, but I thought that lesson might be a little bit too big and a little too overwhelming. Like it would just kind of hit on too many different things at once. And so I opted to break this up into 2 lessons. Now, as a result, I think the lessons are going to be a little bit shorter. We shall see. Usually nobody complains about that. But without further ado, let's go take a look at our first lesson. So I wanted to start off with this exploration activity. And when we do this in class, and now I'm wondering why there's no line on my table right there. That's a little weird. Okay. Anyway, I wanted to start off with this exploration activity in Desmos. And in class, I want everybody to have Desmos out and we'll do it together. So if you're watching the video from home to make up the lesson because you were absent on that day, go ahead and grab Desmos, get that open in another window or get it up on your phone so that you can do the activity along with us like you were in class. Now, if you're watching this to review and you've actually already done the activity, that's a little bit different. So when we go to plot these points, what I want to do is plot them all in the same line. So for the first point, I'm going to type in -2, 0.25, and you can see that Desmos plunks this red dot there. And I'm going to close the parentheses. Now what I want to do is make all of the points in this set the same color. So I'm going to put a comma and then type in the next point. So that would be -1, 0.5. Okay, and what that's going to do if I plot all of the points this way is it's going to keep all the points the same color, and we want that. We don't want all the points different colors because the color is going to help us see something about inverse functions. So we'll go ahead and do 0, 1, and 2, 4, and 3, 8. Okay, so now that is actually a very specific kind of function that we're looking at. We have not studied this family of functions, but we are going to study it fairly soon in the course. So take a moment and just kind of look at what those points are doing. Now, I'm afraid I'm gonna click on the wrong thing. Okay. So now I want to explore some things. So what do you suppose would happen if we switched the x and the y coordinates? Now, maybe you've thought to do this, maybe you've never thought to do it, but take a moment and think about it. If you took every x and every y coordinate and you just switch them, what do you think that would do? Now, it's going to obviously do something. We're going to end up with a different set of points, but we're not randomly shuffling the numbers around. And so because we're doing something very intentional, like switching the x and the y, what we expect is that there's going to be some kind of pattern to what the new points are going to look like when we graph them. And that's really what we're trying to get at in this activity. So we're going to go ahead and switch them. So for the first point, it was -2, 0.25. So what we're going to do is switch those. So we're going to have 0.25, and then the y coordinate would be a -2. Notice that we're not flipping the signs or anything. We are just switching the ordered pairs. So the next one, x would be 0.5 and y would be -1. 0, 1 would become 1, 0. 2, 4 would become 4, 2. And 3, 8 would become 8, 3. Okay, so that's what we think our new set of points are going to look like, or what our new set of points would be. What we want to know is what they are going to look like. So coming over here, I'm going to plot these in the next row down. And what that's going to do is make this second set of points a different color from the first set of points, which is what we wanted. So in this row, we're going to have 0.25 comma -2. Okay, and just take a moment and note where that point is relative to the other points that are on the screen there. My next one will be 0.5 comma -1. Okay. And now instead of 0, 1, we are going to have 1, 0. And right about now, you are probably noticing that there is some kind of pattern here, that when we are switching the X and the Y coordinates, we are not getting random things. And, I've said all year, math is consistent, it's orderly, it follows rules. It's not chaotic, and, we don't have really random things happening. There are patterns to explore. So what do I have here? The next one is going to be the point 4, 2. And before I go ahead and plot that last one, I want you to take a moment and think about where you think it's going to be without even looking at what the ordered pairs are. Looking at the pattern that we see on the screen there, where do you think that other point is going to be? Okay. Everybody have their spot. Where do you think it should be? And then this would be the point 8, 3. Okay, and you see like how close were you? So obviously we have a pattern going on here with our points, and I picked these two relationships actually intentionally as a way of kind of introducing the next unit where we're going to study graphs that look like this. So I do want you to kind of pause and think about that. So we very obviously have a pattern going on here. So this process that we are looking at right here, it finds something called inverse functions, okay? So this idea of flipping the X and the Y, or switching the X and the Y around, will find inverse functions. Now, you can tell that there's a pattern with the graphs here. So that gets into this first thing that we want to know about inverse functions. The graphs of inverses are symmetrical, and I actually don't think I'm going to be able to get to my oh, maybe I can. Symmetrical over the line. I am actually really afraid to write on that because that's right where I would click to change to the next slide, and I don't want to click change to the next slide. If you've watched enough of these videos, you know that this happens a lot. So I'm going to actually put it over here. They're symmetrical over the line y equals x. Yeah, I'm afraid if I tried to write on that line, it would have clicked on the little arrow there. They're symmetrical over the line y equals x. So we've done different kinds of symmetries in this class, like if you flip something over the line or over the x-axis or over the y-axis. This is not a flip over the x or the y-axis, but it is a flip. So what I'm going to do is put in the line y equals x so that you can see it. And let's take a moment and just pay attention to what's happening in this graph. So this right here, this green line, if you're following the laser pointer thingy I have on the screen here, that's our line of symmetry. And every red point has a mirror point that's the same distance away on the other side. Okay, it's the same distance away on the other side. So -2, 0.25, come right across here. This is 0.25, -2. This is -1.5, come right across. This is 0.5, -1. Here is 0, 1, and here is 1, 0. Here is 2, 4, and over here is 4, 2, and then this one is 3, 8, and cutting all the way across is 8, 3. So I really want you to take some time to notice that, because that can come in really handy when you're dealing with the equations or other things. Like I know that there's a question on your homework that's going to ask you to kind of verify some work, and sometimes if you get stuck on the the mechanics or the algebra, you can go to the graph. Like that's allowed for you to go and try to answer a question graphically instead. Okay, so that was that introductory activity. We'll be doing that in class. So hopefully if you're doing this from home that you did actually participate in this, get that practice, typing it in, pausing the video, looking for the patterns and so forth. You're not just putting me on double speed to get the lesson done. All right, so there's a couple of questions that just started pouring outside. There's a couple of practice questions right here. So pause the video and take a moment to work on the practice questions, and then we will go over these together, especially that second one. All right, so the first one here is asking if the point 3, -4 is on the graph of a function, what point must be on the inverse? It must be -4, 3. Okay, so you're just switching the x and the y. Just again, be very cautious about like not moving the signs. Every year I'll ask a question like this on the test, and every year students will flip signs around. Now this next one is tricky. Some of you are going to find this very easy to do. Some of you are going to find this very challenging to do. It just kind of is what your natural aptitude might be for this. I kind of find it challenging. This moving stuff around on the coordinate plane, not my strong point. So we're going to try to sketch the inverse of the graph shown here. Now what we know about inverses is that they are symmetrical over the line y equals x. So the first thing I'm going to do this is I'm going to draw in the line y equals x. So that is going to cut right through here. Okay, I think that was pretty good. And now I can kind of picture what this might look like. Like I'm going to flip some stuff around, but I'm still really bad at this. And so to help me personally be able to do this, what I'm going to do is locate a couple of strategic points that I can see on the existing graph, and I'm going to try to mirror those points and then use that to see if I can get the graph. So I'm going to start with this point right there. That looks like that's the point 0, 1. And so if what I know about inverses is true, then the point 1, 0 should be on the inverse. So that's going to be that point right there. Okay. Now I'm going to look up. I don't know if you guys can see. I can't see it, so I'm sure you can. Oh, there it is. Okay. If you look at that dot right at the top of the little wavy thing we got there, you should see my little pointer. That looks like it might be like 1.5, 2. It's like a little bit over from the 1.5, 2. So I'm going to try to mirror that point and go to 2 and then like 1.5. So maybe like right about here. Okay. So something like that. All right, where else can I go? Well, I'm going to go ahead and draw this part in. Okay, because what is going to happen is that all 3 of those should cross at the same point. So there's one mirror part. I'm going to do the same thing over here, see if I can find some points that are good to work with. Right here, I'm looking over here on the x-axis near where it says 4, if you're having trouble seeing where my little dot is. This looks like 4, and then it's about halfway down a block or up the block. Okay, so that would be, if I switch that, it would be about halfway and then going all the way up here to the 4. Like something like that. Like right about there. That seems maybe about right. Okay, and then let's see if we can get that end point down here. This is 6, and then it goes like about 1.5 blocks. So I'm going to go over here 1.5 blocks over and then up 6, which is going to put me right about there. Okay. And so if I do this sort of well, it's going to curve like that. Oh, I need to make sure I touch the axis. So we'll try that one more time. Let's see if I can. Okay, so we're going to come down here. We're going to go through there. Then we have to touch the axis and then come up. So that's what I would do, is I would just work with a couple of isolated points and then try to get the best graph that I can. And you can tell that that is symmetrical. Like now that the whole thing is there, you can see that the red part has a mirror image with the green part. So now if you're watching this and you're a little concerned, like, oh my word, am I going to have to do this? I'm probably going to have you do it on your homework because I think it's really good practice, and because I also think that by making yourself look at the graph this closely and pay this much attention to the graph and to the symmetry, it's just going to help you learn the concept better. Now, on a test, I am aware that some of you are going to really try to do this and it's still just not going to look right. I am usually, when I've had students do this on a test, I'm usually pretty lenient about there's like certain key things I'm going to look for. Like I might look for the endpoints to be in the right location, and that crossing over, like all three of them need to cross at once. You shouldn't have, different crossing over points, and look for that. But on your final is going to be multiple choice. So you figure, no, like you're not going to have to do this for your final, but you might have to look at 4 different graphs and determine which one is the graph of the inverse. So you would still need to know what you were looking for, even if you don't necessarily have to do it. So keep that in mind. Always keep the learning goal in mind when it comes to doing a problem like this, not just a particular problem. So let's go on over to the next slide. So how do we denote inverse functions? The word denote usually just has to do with notation. Okay, so what's the notation that we use for inverse functions? So this is the denotation for inverse functions. So you might see the f of x version, or you might see the y version. All right, and the way we would read that is like f inverse. Sometimes you'll hear f inverse of x, but a lot of times it's just f inverse or y inverse, is you would just say the word. Now you might have seen that in geometry. In geometry, when you were doing your trigonometry, there's buttons on your calculator like sine, cosine, and so forth. The secondary function on those is the sine, cosine, tangent, and there's like a little -1. And usually when you're introducing that in geometry, a teacher doesn't necessarily go through a lot of explanation as to what that notation means on your calculator. They just tell you what the button does. So sine would find the sine of an angle, but the inverse would find the angle if you knew the sine. Okay, so it would go the other direction. And that, honestly, if you think about that, switching the x and the y, like it's going the other direction. Okay, so one of them you have the angle and you want to find the sine, and then the inverse, you would have the sine and you wanted to go back and find the angle. Okay, now some of you are probably wondering something about this. Where'd my mouse go? There it is. Okay. How do we distinguish this from an exponent? So this looks exactly like an exponent. In fact, the word that we would use there is superscript. Both exponents and inverse notation are called superscripts. Super meaning like above, like that super day is above average, right? So super, and then script is writing. So superscript is writing that is above. They actually do look identical. So how do we distinguish this? How do you know if you're looking at something, whether it should be y to the negative first power or if it's y inverse? And the answer to that is simply the context of the problem. Okay, so we do this all the time in our English language. If I were to say, like I said earlier, it is raining outside, okay? Probably everyone, unless you're new to English, in which case, give that some time. But so is picturing rain, R-A-I-N. And nobody was thinking this kind of reign, like the queen is reigning in England, or I guess they have a king is reigning in England, or this kind of reign, which is, man, you need to rein that in, or the horse's reigns. And how do you know which one of those words reign? I mean, when I said it out loud earlier, oh, it's raining outside, you knew it because of the context, because it doesn't make any sense to picture the King of England reigning outside of my condo here, okay? It just makes no sense. And it's the same thing with this notation. So we know what it is based on the context of the problem. So you look at the rest of the problem, you look at what the directions are asking you to do, and that's going to tip you off. In fact, a lot of times the word inverse will actually be in those directions. All right. All right, so how do we find inverses? I think this is the last topic for this chunk of the lesson. The next chunk of lesson, we're going to go into how do you verify that something is an inverse, and like what do inverse functions actually do? Why are they a thing? So how do we find inverses? Well, the first thing you probably want to do is replace f of x with y if needed. So f of x has its place. It's got its notation. And we've seen in the last couple of lessons with the operations on functions, that you would not want to do that with all of your functions just called y. Okay, that would be confusing because everything would be a y. But f of x notation also has its limitations, and this is really one of them, where it's a little what I would call clunky. So what I'm going to do here first in this problem is I am going to replace my f of x with a y. Okay, and that you don't always have to do. Sometimes it's already going to be a y. So good, yay. Now this next step is going to seem familiar. You are going to exchange all the x's and the y's. You're going to exchange x and y. Now, this particular function and the ones that I'm going to have you do are going to have just one x and one y. Okay, so I'm not going to mess with like what do you do if you have more than one x, which often we do. If you do, all of the x's become a y. So there is one on your homework where you're going to have to look at the work. You're not going to have to do the work. You're just going to have to look at the work and evaluate it. But where that happens. So we literally are going to make this exchange. And if you think back to the introductory problem where we had, say, the point 0, 1, and we had x and y, and then we literally switched them so that the x became the y and the y became the x. This is the variable version of that. So instead of like exchanging the individual ordered pairs, we're exchanging the variables, which is going to exchange all of the ordered pairs. All right. Now we're going to get the new y by itself. So the technical vocab for that is solve for y. Okay, so the directions would say solve for y. When you hear solve for y or solve for x or solve for whatever, it means get that variable by itself. So we need to engage our equation solving skills, and we're going to come over here and look at the y. Okay, we need to get that y all alone. So it's being multiplied by 1/2, and it's also got a 3 being added to it. So we're going to need to undo the multiplication. We're going to need to undo the addition. Please, please, please undo the addition or subtraction first. Okay, that is going to make everything better for you. I promise. So we're going to subtract 3 from both sides. So x minus 3 equals 1/2 y. Now there's a couple ways you can tackle this. I would not write down what I'm about to write down. So I'm going to write something down and then I'm going to erase it. But some of you are going to look at this and you're going to say, okay, that is 1/2 times y. I undo multiplication with division. Therefore, I will divide both sides by 1/2. Now that is technically correct. So if I were to look at your work and I take off points for it, you could come to me and say, Miss Taylor, what's wrong with it? Nothing is wrong with it, but it is ugly and complicated looking. And so we don't like it. So we would like to have a better way to do it. So it falls under that umbrella of really you really want to leave your answer like that. It's not wrong, but there is a better way to do it. So let's go erase this and figure out a better way to do it. In front of the y there, we have 1/2. And I just want to point out that this is 1 divided by 2. Okay, so if I have 1 divided by 2, I could undo dividing by 2 by multiplying by 2. And that is going to be a better way to do it. So I'm going to actually go ahead and multiply by 2. Now, when you multiply by 2, you need to make sure you multiply the entire side by 2 because you're multiplying the entire right side by 2. So you have to make sure you multiply the entire left side by 2 as well. This will distribute through to get 2x minus 6. And then I'll do a little scratch work, but 2 times 1/2 gives you 2 over 2, which is 1. So you're going to have 1y. And then the last step you'll see there is just adjust the notation, because as it is, this is confusing. We have a y at the beginning and we have a y at the end in the same problem, but they are not the same y. This y is 1/2 x plus 3. This one is 2x minus 6. So we'd like to avoid that weird confusion of having 2 different y's there. So what I'm going to do is change that notation over to the inverse notation. And now it is clearer in my work. Okay, this is my original function and this is the inverse function. All right, so that's your process. Replace the f of x with the y, exchange them, solve for the new y, and then adjust your notation when you get to the end. So you can check your work to this using Desmos. So if you have your Desmos handy and you're like, okay, I've done my algebra work for this, I would like to verify that I have the, shoot, I should not have done that. All right, that I have the right function here. So we've got f of x is equal to 1/2 x plus 3, okay? And f, oh, that wasn't quite right. F inverse of x, you can also use y's for these, equals 2x minus 6. And it is not recognizing that notation, is it? F is a function, try using parentheses. I'm just going to delete that. There we go. Okay, so we got the confusing like f of x twice, but okay. Now there's the original function and there's the inverse. Now some of you are going to look at that right away and you're going to be like, yep, that's right. Those are inverses because they have that correct symmetry. Others of you are going to be like, I don't know. Let's go put in that line of symmetry. There it is. Now you can see it better. Okay, so now it's a little bit easier to see that the red line is reflected onto the other side of the green line. And when they switch, it just gets reflected the other way. And notice, again, all 3 lines come together at the same spot. Okay, that's critical when you're looking at graphs of inverses and stuff. Like the function and its inverse should be crossing that line at the same spot. And if you think about the line y equals x, that should make sense. So if you think about the line y equals x, like what's a point on that line? Maybe 3, 3. Well, what happens when you switch the x and the y? Oh, look at that. You get 3, 3 again. So that's why it's on that line that the function and its inverse, they're all just going to converge. Right there, it looks like it's at 6, 6. Okay, if you look at where that is, it looks like they all kind of come together there at 6, 6. Okay. I messed it up trying to graph this thing. So if you're joining us, of course. I have backtracked. There's a caution here. Caution, not all some inverses are not functions, and so we want to be careful with the notation. So this can get really tricky. This can get into where you have like a function, but when you take the inverse of it, you have to like restrict the domain because the original function had some kind of limitation on it that's not going to show up in the algebra. I don't want to get too much into that because you can always go back to Desmos and back to looking at the functions that way if you need help with that. But here's an example. It's y equals x squared. So remember our steps in the process. We're going to change f of x to a y if needed, not needed in this case. So then I will switch the x and the y's. Okay, so we have x equals y squared. Now, we know that we want to get the y by itself. The y is being squared, and we know we can undo squaring with a square root. But you can probably tell by the way I'm talking, like, careful. Remember when we had like 25 is equal to x squared? And when we were looking at the equation that way, we had to remember to do plus or minus because both 5 and -5, when you square them, would give you 25. Because that function or that equation x equals y squared has the same form, we need to remember the same thing. So when we go to write this, we need to make sure we have plus or minus the square root of x. And then my inverse notation is going to come in that last step. Let's see if I can do that a little bit better. There we go. Okay, so now we want to look at this on Desmos. And this is about where like I got myself kicked over to the next slide. So this is the original function, the y equals x squared. When I go to do the inverse, I actually can't do it both on the same line as far as I know. What happened before, which you guys didn't notice because I've recorded over it, but I was trying to find if there was a plus or minus symbol. And I don't think there was. So we're going to have to do this in two separate ones. We're going to have to do positive the square root of x. And then on the next line down, we'll have to do the negative square root of x. And you can see now that, like, remember this is all the same function. Let me see if I can change the color. No. Nope, I guess not. There is a way to change the color on that, but I'm not going to bother with it right now. But notice that this function over here, the sideways parabola, is not a function. Okay, yeah, which I think I just said that wrong, and I apologize. But this is not an actual function. It doesn't pass the vertical line test because of that plus or minus. And just in case you wanted to see, is this really, like, are these really inverse functions? I'm going to go ahead and put the line y equals x in there, and now you can see. That, yep, we have that symmetry there. So even though the red one is a function, the inverse of it was not a function. So just be a little careful when you're using that f of x notation, that you don't want to assume that everything's an inverse. Now, if you had started with y equals the square root of x, then when you go to undo that, you're going to end up with y equals x squared, and you actually have to put a restriction on the domain. That is something that I covered a lot in my college algebra classes, but not typically in Algebra 2. Oh, that's right. I have to stop the recording again. Okay, so last but not least, we have a couple of practice problems. So just find the inverses on those functions. If you are following along from home, obviously pause the video and work these out. See if you can find these inverses on your own, and then you can unpause the video, and I will go over them in the video because I think this is something that, I should go over the steps too. All right, so hopefully you paused your video. So looking at the first one, I'm going to start off by changing that f of x to a y, and then switching the x and the y. And now I want to get the new y by itself. So I've got a times 2 and I have a minus 3. I'm going to take care of that minus 3 first. So we're going to add 3 to both sides, which is going to give us x plus 3 equals 2y. And then I'll undo the multiplication with the division. Just make sure that you divide the whole thing by 2. And when I rewrite this, I'm going to go change my notation to match. So we have x plus 3 over 2. Some of you might do this. You might do 1/2 x plus 3/2. That's only helpful really if you're going to graph it by hand. Okay, you would want it in that slope intercept form. There's a plus sign missing. There is a plus sign, like there we go. 1/2 x plus 3/2. So I don't think I would do that. I think I personally would leave it like that. Again, because the more steps you do, the greater the chances are of something going wrong. For the second one, that one is already in the right form. So we're just going to go ahead and switch the x and the y. And now we've got some stuff happening to the y there. We're multiplying by -2/3, and we're also adding a 1. So we're going to deal with that 1 first by subtracting 1. And then to get rid of that 2/3, you can divide by -2/3, but it's going to be awful. I'm actually going to erase that, and I'm going to rewrite it with a little bit more space. Because I know what I'm going to do. I'm going to multiply by -3/2. Okay, now if you're like, wait a minute, Miss Taylor, why? Because if you go up here, follow along up here, I'm going to be in orange. -3/2 times -2/3. Well, -3 times -2 is +6. 2 times 3 is +6. 6 divided by 6 is 1, and that's going to give me that 1y that I wanted. And then you can distribute this through. I actually think you're probably okay leaving it. There's a time to distribute stuff through, and then a time when maybe we don't care as much. If you do distribute it through, it's -3/2 x plus 3/2. So that I'll leave that up to you. All right, so that should have given you an opportunity to check your work. Now, there is a homework assignment for this. If you look at the top of the homework assignment, it says that it is due after the second lesson. But what you should do is you should go through that homework assignment and see what of those questions you can answer now based on today's lesson, and then the next lesson will go and we'll cover the rest of that. But that way you'll be able to ask some questions in the meantime. All right, as always, you guys know where to find me if you have questions.